kick it off. So, our first speaker in the engineering track today is Alexander Tarlinder. Alexander has been at CRISP for over 12 years. And you can tell from the title of the talk here on the screen that Alexander likes to speak the truth. And I'm sure we'll experience some of that today. It can be, I hope it will be very blunt. That's what I love about your talks. Alexander is a programmer, also a Scrum Master and a professional coach. He's also written the book on developer testing, or as it's sometimes called, the book that teaches developers how to test. Curious fact about Alexander, he's built a small data center in his home. I'm proud to call Alexander my friend. Alexander, the room is yours.
Thank you. Likewise, Max. I mean, your intros get better and better every year, and I'm always blushing. So I mean, it's hard to actually pick up any topic, any trail after Henrik. So I'm gonna start giving you the caveat. If what Henrik says extrapolates, I need to change always into for the next year, but it's better than nothing. And also, that being said, software is still like a lot about people. It's so we've got our year to come. So anyway, so let's kick it off with always. I mean, that's quite a presumptuous title, and of course, I mean, I need to catch people's attention. And if your main problems at work revolve around soldering pieces onto a PCB and doing like NAND logic, parts of this talk may not be relevant to you. Likewise, if your big problem is how do I optimize my vertex shader, some parts of this talk may not be relevant to you. But if you've got your average application, which somewhere accepts some kind of user input through a mobile or web interface, and somehow writes data to some database or any kind of storage, like imagine your everyday application, this will probably give you some pointers, or that's what that's what I'm hoping for. So this is going to be a quick talk. I mean, every single of these points actually deserves like a half-day talk. And also, I've kind of removed all the things that don't work. Spoiler alert, if you want things that never work, it's basically duplication and like don't duplicate stuff and don't use manual test data. But let's get to things that work. So these are a couple of things in increasing order of interest, I would say. I urge you to pay attention to the last point. People love specific numbers. People don't like it depends on answers. So you've got a specific answer. You need 14 end-to-end tests, and I will convince you of why that is. So okay, what always works? So again, this is from the perspective of like you entering an organization, everything is a mess and you need to kind of start digging somewhere. So if you do any of these things, you will kind of never be wrong in a way, in a sense. So the first thing is like, you can never lose by paying attention to naming. And if you look at an average code base, the most powerful refactoring you can apply is just the rename refactoring. I mean, bad names are so extremely confusing, and what we try to kind of aim at when naming things properly is to actually decrease our own cognitive load, so to say. We don't want to maintain a mental dictionary where we translate different concepts between what people in the organization are saying and ourselves. So obviously, we do want to talk to our end users or users in the organization. We want to understand our stakeholders, and there are these big fields of domain-driven design, behavior-driven design, which are basically and object orientation for that matter, which are basically about naming things. You may have heard the concept of the ubiquitous language. Again, just finding the language in the organization that people can agree on, like in Swedish, it would be a shovel is a shovel, right? So like, don't rename the shovel to Batmobile. I don't know. So it's a huge thing. Like you speaking the same language as the users of your software, as the members of your team. And actually, I mean, I can guarantee, clickbait guarantee, that if you use poor names, you're gonna trip yourself up, like your future self. If you find this funny name, which you incorporate in your code, in 1 month you will be very, very disappointed with yourself. So names are super important. You can't do wrong by renaming things. And as I've written, never ever invent names. Here's a slide I'm using for like in my clean code training. This is like a summary of what you would find in material and clean code. And again, it's very much, these are more concrete pointers to what good and bad names look like. And if we have this cluster here of descriptive, specific, and unambiguous, basically that would mean like pick a name that's relevant, right? Pick something useful. This one is cute names is an advice against using names which you find funny today, but which you won't find funny tomorrow, or names that other people have found funny at some point in time. That doesn't work. Mental mapping is a huge thing. Again, it's about not coming up with your own names, creating aliases. It's just better to ask your users, ask your colleagues, ChatGPT for that matter, for a proper name. And I'm sorry, I'm getting distracted. My daughter is crying somewhere in the kitchen. Obviously, names need to be correctly spelled. It's extremely, extremely annoying to see misspelled names, I bet. This is like the list of bad names. Never have them in your code. That's very, very simple. So you can see that those are basically generic names, right? Which there is obviously a domain where these names are relevant. I mean, if you are in the domain of threads and threading, maybe worker is a fantastic name, right? But in 99% of the cases, worker is a lousy name. Get is particularly dangerous because get means like everything. It can mean like pick, fetch, find. There's so many things get can mean, and get is usually, if you do Java, it's kind of in the middle of the Java bean naming convention. So get is a very loaded term. Whenever I run this this slide with people are kind of always assuming that manager is not really the general class, which we have not bothered to name, but it's really an object like this, a class describing the role of a manager in like a payroll system or something. So that's very, very confusing. So I bet this list can grow larger, but basically never ever use these names and you will be fine. You can't do wrong. Next thing is strict typing. And strict typing is super, super important for many reasons. And I still have not found the like super good counter argument against it. Like some people say it's easier, you kind of do things faster if you avoid strict typing, but I mean, it saves you so much. And I mean, if you've got a strictly typed language, your IDE will help you, right? The other thing is, we're going to see an example of this soon, but basically, if you remove typing of around variables, everything is just like a floating entity. It's just something, right? Any variable is something. It can be this, it can be that. It means, I'm using the phrase cognitive load a second time today. It means that it's up to you to kind of keep track of what this something is at a specific point in time. Why typing makes testing easier is a bit of an academical question. but it has to do with the number of the size of input and output domains and the number of test cases you would need to employ to actually test through these domains. And I would argue that typing increases security, because by moving away from this unquantifiable string or buffer or number into something which is like a proper entity, you can get rid of things like buffer overflows and SQL injection like attacks and stuff like that, because you have you'll see what I mean in just a few slides, but you have removed all the bad input as you've moved to proper type. So again, you can't do wrong by typing. Suppose you are in a world where nothing is typed. I'm just kind of reiterating my point here, that at some point you are accepting user input. It's not typed. It can be a string, it can be a number, anything. I mean, the first thing you need to do is validate to kind of get a grasp of what that input is. And then you're going to call something, some operation. It doesn't really matter what it is. I mean, I've written a call stack of 3 functions here. And again, in this function, as this guy, function A, calls function B, that thing, it doesn't know who's called it. So it again needs to kind of check what is input. Is it in a, does it conform to a specific format? Is it within an expected range, and so on? And so it goes. So this means that at no point in your code are you really trusting the contents of your variables if you have an untyped language, and that's super, super dangerous. Looking at, I found this beautiful matrix from JavaScript, and it kind of illustrates the point a little, at least. And the author of this, I'm giving credit what credit is due, draws the conclusion: always use the 3 equals, which kind of makes sure that correct things are being compared. But I mean, look, for example, I mean, this is my favorite. This is my favorite guy. You compare the empty array with the empty string, and boom, it's equal. And that's actually what you get in untyped languages. You have to be prepared to handle this in one esoteric way or another. So I would really recommend strict typing. Object orientation is fantastic for creating strict typing. I happen to work in the telecom domain, and as you can see, there's like a lot of number and strings in our domain, right? But all of these things, like my favorite example would be, for example, why not VLANs? It's a virtual, it's an identifier describing, let's call it just a virtual network to keep it simple. And had this been a number, like any number, -1 or 16 million or whatever, we would never trust it. We would have to write if VLAN is larger than 0, less than 4,000, blah, blah, blah. Instead, if we create an object which is called VLAN, and in the constructor of this class, the VLAN class, we perform these validations. We perform them once. This is where we increase security, because this is where we have the chance to stop invalid input, malicious input for that matter. And we know that throughout the system, everything called VLAN is actually a VLAN. We can really, really trust that type. And that's really a big thing. And that's why I'm really recommending that if you're programming in an object-oriented language, like go nuts, turn everything into an object. As soon as you've got one single if that you would use on a variable of that type, stick it into a class. Unit testing, I'm gonna keep this one short and sweet. I mean, it's 2023, I shouldn't be kicking in open doors. So Unit testing isn't super good for testing, right? That we kind of know. I mean, usually unit tests are written by the same developer who has written the code, so obviously we can't really test that much. However, they are fantastic for maintaining your safety net, for refactoring, for regression testing. So that's where they shine. And like a little recommendation here is that if you spend some time and really use like proper, realistic test data in your unit tests, you're going to get fantastic documentation of your system. It doesn't only apply to unit tests, it applies to any kind of tests. But like, spend some seconds using actual data, and we're back to this thing about language and naming. Like, don't have Calicula. Use like a proper name for whatever you're sticking into the variable. But still here, if we disregard all these things, unit tests will still help your code to it will stop your code from being a complete mess. So the point here is, why does unit testing always work? It always works because if you start writing unit tests, you will not dig whatever hole you're in. You're not going to make that hole deeper. So the advice is obviously not, if you've got a mess of legacy, start writing unit tests at random places in the code. That usually doesn't work, or never works. Maybe even speaking of things that never work. But like, develop new code with unit tests, and you will stop future badness. You will not make your hole any deeper. The next thing, I mean, which I've never found a case, like a counter case to this one either. So test data is a super hot topic. If you go to any testing conference, people will have so many complaints and theories about test data. And I mean, from a developer perspective, test data is the kind of data you would feed into unit tests, integration tests, and end-to-end tests. And I've seen that whenever you have this situation, speaking of things that never work, like never work with static test data, because it ages and it gets obsolete and it's really hard to keep up to date. But we do have a solution to this too. So the builder pattern is a pattern, like an old design pattern, kind of Gang of Four type of design pattern, which is a creational pattern. So you probably have heard of singletons and factories and so on. What makes builder different from those is that it rests on the assumption that whatever you create has a set of reasonable default values. And that is exactly what test data has. That's what's so fantastic about builder pattern as test data. Because in the majority of cases, if you've got a unit tests, or any kind of test for that matter, usually you don't care. Like if you've got your average system, for example, and this average system has a customer, you don't care. Most of the time, you don't really care about the 20 fields of the customer. You care either about one or two of the attributes of the customer, or you care about the fact that there is a customer. You just want a customer, like, be done with it, give me a customer, and you want to test something else because something is connected to that customer. And this is where builder shines. So I'm just giving you a snippet of Python code. I happen to be programming in Python right now. This is a bit over verbose, just like an example code would be here. But given that we have a customer with an address, we've got a set of reasonable defaults. Speaking of realistic test data, don't do this. I'm just checking that everyone's still with me at this point. Don't do this. And if you've got a test, you can, I mean, just calling like customer builder.build would give you a customer. It would give you a valid customer. If you want to modify that customer, you use your you use this method chaining. So this is trivial, right? But what's interesting about this? There are three interesting things about this this way of setting up test data. One is the fact that you can do this for unit tests and for something that goes into a database. You stick your favorite persistence kind of thing into this builder, and you can have these things persisted. Like the builder can persist it for you. The other thing is that the builder can, and there will be, speaking of never duplicate things, but at least the builder can actually follow a set of rules. It can create valid objects. You can incorporate, yes, you will be duplicating business logic, that is true, but you will be duplicating a simpler version of business logic, and it can kind of hide and abstract away any kind of funny business rules you've got around your entities, stuff being tested. You can put that into your builder. And that's also fantastic, which means that you will get valid objects. That is a trade-off. It's true, you are duplicating your business logic into your builder. Let's say, for example, that a simple example, all customers are required to have a street number. Now that's a very stupid example, because obviously not all streets have street numbers, but that is something you can put into your builder, like a constraint like this. And whenever you create an object, whenever you create test data with this builder, it's going to give you something valid. The third and most super powerful thing is this: it shields your tests from refactoring to central entities. I mean, imagine if you add another field to a customer, like a mandatory field to a customer, like a member attribute of that class. The builder is the only place you need to change. Similarly, if you add a field to the database, again, the builder is the only place you need to change, and that's fantastic. I mean, you've got this test data shielded by this pattern. There is also like extra material on this saying that if you can't do this, you can at least abstract existing resources using this this approach. But I'm going to save that for later talk. Next thing that always works is 4+1 architectural descriptions. Again, seeing how people work with architecture in the wild, there are 3 modes to work with architecture. Some of our clients have nothing. Some have these really ambitious documents. They don't necessarily follow an architectural standard, but they are certainly ambitious. I would argue that the most prevalent style of documenting architecture is the so-called one-pager. I would love to show you a one-pager, but obviously for confidentiality reasons, I can't do that. But the one-pager, I mean, if you enter an organization like or a new team, or just you can kind of just you're just new somewhere and you want to learn about the architecture, you ask people for architecture, you're gonna get the one-pager. And by the one-pager, I mean sometimes it is literally one page, like one document, one page. Sometimes it's 2 pages, but I mean it's very close to 1 page. And what you're going to see in this one-pager is a mishmash of everything. You're going to see use cases, you're going to see protocol versions, you're going to see languages, you're going to see physical deployments, you're going to see IP addresses, you're going to see everything, right? Like framework version, Spring, 3. Whatever, I don't know. So, and why it's certainly better than nothing, they are hard. So the way out of this is, first you kind of need to realize that why is a one-pager a not very good choice? Well, it's because it's very hard to look at something as complex as an architecture from one perspective. That's why there is the concept of the concept of the view is very, very central to computer architecture. So if you kind of realize that you need views, the next question is how many views? So you can ask the big internet, and you can get something with a lot of views. This is the Zachman framework. That's a lot of views. It is actually, this is like a real architectural framework, right? I would suggest that you don't start here. I would suggest that you start here, in a place where you've got 4 views plus 1 view. And this is something at least a developer can relate to very, very easily, because instead of 1 page, you need 4 pages. And the way you work with this is put that on a wiki, like for every one of those 4 or 5, whatever, pick your poison. So create a wiki page. So create a wiki page called development view, and boom, you stick your coding conventions, you stick your diagrams, design decisions, just put them there. See how that goes. We kind of tend to know how to and where to deploy our system. Create a page called physical view, stick your hardware, IP addresses, servers, clusters. Now everything is kind of Dockerized or in cloud. Never mind, put that into the physical view, whatever. Not that important. Don't put it in the development view, put it in the physical view. Soon enough, you will be asked to present a sketch of your system in a bigger context. So put your integrations, like the picture, where you draw this. I've got my 5 microservices, my message bus, my databases. Put that into the logical view. Finally, the one which I find in a way hardest is the process view. But if you kind of ask yourself, who are the users of the system, and what key operations does our system support? Stick that into the process view. And like the general advice is here, like keep this small. I mean, you can literally start by having these as single pages, but at least you've got a structure. And as this grows, you may create subsections. But the thing is here, this always kind of works because it requires 4 pages. It doesn't require like a formal architecture training. It's just a matter of sorting things into four big categories. And scenarios, lastly, you can really wait to fill in that one. It's again the core use cases. Those are, by the way, the thing that you would feed into your end-to-end tests. Okay, 2 more to go. So hexagonal-ish architectures. As I read up on this, we tend to speak of onion architectures because hexagonal is very, very confusing. But something that always works is isolating. I mean, if you've got a system which is not a complete spaghetti, some parts of the system are more pleasant to work with than others. The parts that are not pleasant to work with are actually the ones on the picture. And sorry, UI. Yes, if you are a UI designer, you find this pleasant. That's not really the point here. The point here is that these things usually require third-party components. They need to integrate. These third-party components change. They are buggy. There is network connectivity. There's external dependencies. You just want these things to work. And again, sorry, the caveat, I mean, if you are a UI-heavy organization, that might not be the case for you. But the key takeaway is that these things are hard to test. They rely on third-party stuff, and they're generally cumbersome to work with. As opposed to this, as we've established, I mean, we name things well, we type things properly, and we unit test them. And that's what we put at the core of our application. And that's what an onion architecture is, or ports. You can call it hexagonal ports and adapters. But the important thing is that you've got this beautiful core, which is super, super unit testable, which is super easy to maintain. And like every operation in this system can be seen as something passing through that core. So if you want to test these things, or even like just reason about this, you would see that you would see an operation as, okay, so a user enters something. Okay, good. So it starts at the UI, it starts at the edge here, passes through my beautiful, well-tested strictly typed core, and goes out to this gunk. So this this always works because it lets you isolate away the hard stuff here. You put this in a very specific box. You still need your tests here, but your tests will be pairwise. That's the big thing. They will be, you will integrate your tests will be integration tests, but it's going to be a test like between a set of entities and the database, between some kind of service function and what happens on the bus. It's never going to be something that just goes back and forth across this core. That's why you would want this. Last but not least, having 14 end-to-end tests. Yes, you want 14 end-to-end tests. What is an end-to-end test? It's a test that executes from a user's perspective. So basically, you've got lousy controllability of your system. You've got lousy observability. They are slow. They are brittle as hell. I mean, if something breaks in an end-to-end test, you get no info whatsoever, except for something broke. And they are, all of these together makes them very expensive to develop. However, you do want them because obviously they are your super, super good safety net for refactorings. Like if you've got nothing else going on in your system, you want end-to-end tests. If you're taking over a legacy system, that's what you want. And Max, my time manager, I've got one more slide. That's it. So I'm really at the end of my talk. I'm really making the argument that you do need end-to-end tests, because I mean they are the ones orchestrating all your components. They are actually, I mean, those will be your smoke tests. But how many do you need? So I would argue you don't want 0. I've been in an organization that has 1,500, but where would you be between 0 and 1,500? So here's what's happening. As you go from 0, as you kind of move from left to right on this scale here, your execution time of your test suite increases, and you want to keep that short, right? You have invested in your infrastructure. The infrastructure is complicated. You're orchestrating containers. You're running these tests. You may be running some kind of UI stuff. So you are getting a payback for setting up this infrastructure. You obviously cover the an increasing number of scenarios, which may be a good thing, right? Like common, you do want to cover the common user scenarios with your end-to-end test because you do want the safety net. The danger of end-to-end tests is that they tend to strangle the number of lower level tests. They are very easy to copy, and they actually, I mean, if you are here with 1,500 end-to-end tests, you obviously haven't trusted or written your unit tests because you never need 1,500 end-to-end tests. So what you have done is you have stopped writing your unit and integration tests. You have put all your eggs in the basket of end-to-end tests. So as you see, we've got a few opposing forces here. And as like a final point on this talk, I would say that if you weigh these arguments against each other, you arrive at the conclusion that you need 14 end-to-end tests. Quick recap. Naming, don't trip yourself up in the future. Help yourself finding stuff. Help yourself testing. Don't write prevents you from writing bad code, isolates you from changes, and isolates you from rotting test data. Architecture made simple. Dirt is contained into outer layers of the onions, and the optimum number of end-to-end tests. And I'm done.
Thank you so much, Alexander. That was really good. I can offer one detail on the 14 end-to-end tests. The company where I'm working at currently, Warner Brothers Discovery, we have this exact problem with a architecture that started off with people writing maybe only end-to-end tests, and we're struggling to keep them down. We definitely have hundreds for a single service. But we have to stop so that we can have a bit of a break. Thank you again. And for everyone in the room, please join Frederick's talk at 14:45. So short break for everyone, and see you soon. Bye-bye.